Hello and welcome to the channel Understanding.Concepts.Of.Physics. We are here to discuss about Angular Simple Harmonic Motion today. We are on the verge to end the oscillation chapter, leaving but one topic of magnetic needle. Probably that would be done in the next video. And in the today's video, we are going to discuss something about Angular Simple Harmonic Motion. So let's just start. So angular simple harmonic motion is a periodic motion. So even the simple harmonic motion was also a periodic motion. Angular simple harmonic motion is also a periodic motion in which the torque, so if you remember simple harmonic motion, the force was directly proportional to displacement. In this, the torque is directly proportional to the angular displacement. So you get force is directly proportional to minus x. Here you will get torque is directly proportional to angular displacement, and they always point in the opposite direction. That's the reason why we get torque is directly proportional to minus theta. So if you see, torque is inversely directly proportional to theta and always in the opposite direction. That's what the mathematical version for angular simple harmonic motion is. Now we are going to derive a simple equation for angular simple harmonic motion. So let's say we have this rigid support. Okay, this is the support, and we have this string. We have tied a string, and this is a disk of some thickness, and it is at rest when the mark, and we are going to mark the disk with some chalk or some marker, and that's this mark, the red one. Now if the disk is rotated in any one particular direction, either this side or either this side, and released, then the disk is going to oscillate like back and forth. It will rotate like this, and then it will go back like this. It will go back like this, and then it will come back like this. So it will keep on doing that. So the angle which is discovering from its mean position is called as the angular displacement, theta, and this is the extreme position, and this is also the extreme position. Okay, so here we can say that k torque is equal to minus of theta. It is directly depending on displacement. The more you make the angle, the faster it is going to come, the more torque it is, restoring torque it is going to get developed. So this torque is basically the restoring torque, which is trying to bring the disk to its original position. So this is the restoring torque. So maybe I can just write it over here, okay, that this is not anything but it is a restoring torque. So restoring torque, this is nothing but a restoring torque. Okay, now to remove the proportionality sign, proportionality, okay, so there is also a proportionality sign. So this should not be equal to, I just made a error over here, it should be proportionality sign. So in order to remove this proportionality sign, I'll need to multiply by a constant, and that constant happens to be c. Now this constant c is called as the twist constant, and if I wish to find out the value of c, I'll take this theta on the other side. So I get c is equal to tau upon theta. So this is basically your tau upon theta. So now you see, okay, where has the minus sign gone? Now see, if you remember that minus sign is just showing that the torque and theta is in the opposite direction. So if I take a magnitude and if I take a minus sign over here, then I'll get the answer to be as positive. So basically c is a number, and minus sign is just showing that they both are in the opposite direction. Then comes unit. Now torque ka unit is Newton meter, and theta, that is angle, is the unit is in radians. So c is a twist constant, and the formula for twist constant is torque upon theta, and Newton meter per radian is the unit for that. And then the dimension, if you see, whatever the dimension for torque is, the same dimension will work for the twist constant as well. The reason is the radian is unit for angle, and angle does not have any dimension. It's a supplementary quantity. So Newton meter is basically the dimension for same as work done as well, energy as well. L2 m1 t minus 2 would be the dimension for torque as well as twist constant. Now we'll derive a small equation in this. Let's say, okay, we also know that, okay, from your chapter on rotational dynamics, that torque is equal to I into alpha, where I stands for moment of inertia. I stands for moment of inertia, and alpha Alpha stands for angular acceleration. Angular acceleration. Now this is the formula which I have utilized from your circular motion. So wherever there is torque, I can replace as I alpha. So in my this formula, torque is equal to minus c theta. In place of tau, I will write as I alpha. So I get I alpha equal to minus of c theta. Now I'll bring this minus c theta on the other side, so I'll get plus c theta, which is equal to 0. Now as you know that if you differentiate displacement, you get velocity. If you differentiate velocity, you get acceleration. If you integrate acceleration, you get velocity, and if you integrate velocity, you get displacement. Same it works for rotational motion as well. If you differentiate angular displacement, you get angular velocity. If you differentiate angular velocity, you get angular acceleration. And if you integrate angular acceleration, you get angular velocity, and if you integrate angular velocity, you get angular displacement. So basically, if you differentiate 2 times theta, if you differentiate theta 2 times 1 and 2, then you get alpha. So wherever there is an alpha, I will write as derivative of theta with respect to time, but only twice. So alpha is written as d square theta by dt square plus c theta equal to 0. Now this equation is called as the differential equation of an angular simple harmonic motion. If you remember, our simple harmonic differential equation was m d square x by dt square plus k x is equal to 0, which is very similar to this equation because I is replaced by m, theta is replaced by x, time is time, c is replaced by k, and theta is replaced by x. Now let's see how do you go ahead with this. Also I can find out the value of alpha as well. So if you see this equation, this particular equation, or maybe this particular equation, okay, this one, if I remove this I on the other side, I'll get minus c theta upon I. This is the value of alpha, that is the angular acceleration. Okay, now there is something called as time period, and now time period ka equation I have derived somewhere maybe at this point. If you see, time period is equal to root of m by k, and also time period is equal to root of x by acceleration. Now this is one of the equations which I have derived in previous some previous video, and I'm using that formula here as well. So t, that is time period, is equal to 2 pi root of m by k. Now what we can analyze is m has to be replaced by moment of inertia. So m can be replaced as moment of inertia. K, which is the spring constant, will be replaced as the twist constant. So if you see, t would be equal to 2 pi root of I by c, and here t is equal to 2 pi root of x by acceleration. This has been proved in some other video. Now x can be replaced as theta, that is angular displacement, and linear acceleration will become angular acceleration. Linear displacement became angular displacement, linear acceleration became angular acceleration. So these are also the formulas which we can utilize in solving problems. But yes, to a large extent we have just similarly done that what angular simple harmonic motion is. So this is all about angular simple harmonic motion, and we can start with the last topic of oscillations in the next video, which is the magnetic needle in an external uniform magnetic field. In case you are still with me, then subscribe the channel in case you have not done so, and keep the videos watching from the playlist of the entire chapter. You will get a link of that, and definitely you will benefit the most out of it. Thank you so much. Have a nice day. Bye.